very quickly about these classes of models called generative adversarial networks. They're about a couple of years old, but it's a different way of thinking about generative models. And then I'd like to also tell you a little bit about model evaluation. How do we actually evaluate these models a little bit more reliably? So in generative adversarial networks, there is not really explicit definition of the density for P of x. You only need to be able to sample from it. And what's interesting in these kinds of models is there is no variational learning, there's no maximum likelihood estimation, there's no Markov chain Monte Carlo, so what's happening here? And the way you can do learning in these models is you can do it by playing a game. And some of you who've seen these kinds of models, they're becoming very popular because they actually work remarkably well, surprisingly well. And the idea is the following. You're setting up a game between two players. You have a discriminator and you have a generator. Okay? So the role of the discriminator, and think of discriminator as just a neural net or a convolutional net or some kind of model. What it's trying to do is it's just trying to discriminate between a sample drawn from the data distribution or a sample drawn from your generative model. Okay? So the discriminator is just basically trying to say what's the difference between the two. And the generator basically is trying to fool the discriminator by generating samples that are hard for this discriminator to differentiate between the true samples and generated samples, right? So it's almost like a game between the two players. Let me show you intuitively what these systems are doing. So let's say I give you the actual image, right? That's my data. So X is sample from the data. You push it through the neural network, it's a convolutional neural network or neural network, and D attempts to output 1 to say this sample is from data. It's coming from the data distribution. That's the true sample. On the other hand, you have a generator, and the generator in this case, much like the variational encoders that we've seen so far, Z is typically sampled from some Gaussian distribution, you pass it through nonlinearities, and then you output X. Okay? So that's a sample from the generative model. And then the idea is that you take this sample, you pass it through the discriminator, it has to be differentiable discriminator, and you want to output 0. Right? So the role of the discriminator to say, I want for the real data to output 1, for the fake data I want to output 0. Right? And the role of the generator is to say, how do I change parameters of this model so that when I plug this sample into my discriminator, the discriminator will output 1. Right? Does that make sense? So that's basically the only caveat is that you actually never sample, there's no noise model on the X. So the noise model goes in, you output, this is deterministic, this is deterministic. So this entire operation is deterministic, and it has to be differentiable. Right? So when you set up the network, you're basically setting up the following function. So you have a min-max setting. Let's look at what it does. So from samples generated from the data, you're basically maximizing D of X, so you're maximizing parameters of the discriminator. Right? So you want to be able to output 1 for samples drawn from the data. And in this case, this is just one formulation. In this case, samples that are drawn from the generator, you want to basically maximize 1 minus D. So you want D to be close to 0. Right? So when you're optimizing parameters of D, this has parameters here, you want for the fake data D to be 0, and for the real data D to be 1. Right? And then there is a mean operation here, which is the generator is essentially trying to take the minimum of this thing, which is to say, how can I change parameters of this model so that the output of the discriminator would be 1? Right? Because if it's close to 1, then that's the minimum that I'm achieving. So the whole setting, and there are a bunch of different formulations of this particular, but that's probably the most general, the most people using that particular formulation. And so you set up the problem where you have these two optimization problems. You fix G, you optimize for discriminator. Given discriminator, you optimize for generator. Generally, it's kind of there are some problems when you're training these systems. They are a little bit unstable, so you have to be careful how you're training it. But nonetheless, the optimal strategy is for discriminator to have this property, right? It's probability for any particular x, it's probability under the data, divided p of data plus p of model. Generally, the optimum, it sort of becomes basically 0.5. So if your model is always confusing things, then it's good. Now, this particular formulation, it's fairly easy. Again, the trick is that you have to be able to backpropagate through these operations, right? And there's been just a few models. So this is something that's called deconvolutional GAN architecture, which is you take a code which is sampled from.
What happens if you plug in this optimal discriminator in the formula and then only solve for one later?
Well, you have to know what this is. Right. So you generally don't know what that is. But let's see. So here, let's say you have a 10-dimensional code, which is typically generated from Gaussian distribution. A Gaussian distribution, you pass it through multiple layers of convolutions, you get the image. That's your generative model. You take this image, you plug it into the discriminator, which is again convolutional, some form of a convolutional neural net, and it just tries to differentiate between the two, right? And it turns out these models give remarkably good results. So this is trained on bedroom sets, and I'm missing this is work from Alec Radford. If you look at these bedroom scenes, these look surprisingly good. Being able to generate realistic-looking bedrooms is very hard, but it does do something reasonable. This is done on the CFAR dataset. These are just generic objects. I think there are 100 classes, and you can see this is what the training samples look like. This is what generated samples look like. So you can see it also picks up a lot of structures. So that's, again, very impressive result that you can get that. On ImageNet, you can train these models on ImageNet, and sort of you see some objects, so it's generating something. Now, one question is the model just memorizing these things? That becomes a big question. Is it just part of the training data? And that still is an open question. Is the model just memorizing, so it's just some kind of taking the training data, changing it a little bit and displaying it to you? Or is it really actually generating these images? And for any of people who worked in generative models of images, being able to generate consistency, like there is a bus here, there is a ship here, is actually very difficult.
Why wouldn't it? Would it be optimal to copy?
Yes, it would be optimal to copy.
So I don't understand.
No, but you have to represent it as a neural network, right?
So obviously you have to use some kind of regularization to make sure that you're just not memorizing. Right. The other thing is that, again, the role of the discriminator is to discriminate between training and fake.
But it can be.
But in principle, it can memorize. That's the problem of overfitting.
Yeah, no, but that's regularization. That's the mystery of all the neural networks.
Sure.
That they could memorize, but they don't.
Well, sometimes they do. So, sometimes when I look at some of these results, it also becomes there's like, is this coming from the training set? It looks like a truck. Maybe what happens is there's something like that in the training set with a few tweaks, you're generating a truck, right? So it still is a question. Are these just training examples? You're just memorizing and tweaking them a little bit, or are these truly generative models of images?
But the number of pictures on the right is much larger than the number of training pictures. The number of pictures generated is much larger.
But there could be noise versions, right?
There could be noise versions, right? So imagine that I take it.
You could define a distance between and count.
It's very difficult to define the distance in the pixel space, right? Because if I generate an object and I move that object 2 pixels to the right, the distance between these two images is going to be very big, right? So, or if I change, so there is still an open question of what these models, how do we evaluate these models, and that's not a very trivial task. Yeah, there's a question.
I came in late, so maybe someone already asked this, but have people tried to? Maybe it just makes no sense, but have people tried to use this to maybe train some kind of pseudorandom generator or something?
Pseudorandom generator for what?
Well, like I don't know. You have some generator which is taking in some small input and trying to, you basically train it on random strings as
A
your.
cryptographic thing.
No, I don't think people have tried that.
Actually, they have. So Abadi, yeah, the Google people, they've done things like this. Yeah, it was a signature scheme or some such thing. Yeah, which they embedded using it.
I see. Okay.
Yeah, Abadi is the theorist model name.
But here's some examples, just some cherry-picked examples. This is some of the things that the model is generating, right? So it generates two heads, and I think that's actually is good because that means that the model is at least trying to generate something that's different from the training set, right? Which to me is always means that there is something there, that it's not just taking training examples, adding some noise, and then displaying it.
It looks like you're on an LSD trip.
Yes, that's right.
I wouldn't know. Why couldn't you just?
I don't know.
Why couldn't you just search through to see if it had just memorized something that was in the
Because it's very hard. It's the distance between the images. It's very hard to say. Is that just a? It's very, because it's if you add some noise and if the model just.
So couldn't you just take that truck that you saw in the other one and just look through all your training things and see if there's a truck?
I mean, potentially they could be, but again, if it just changes a little bit of a color, if it changes, takes these pixels and makes them black versus white, then that's it. You will not find the nearest neighbors here because the distance in the pixel space is going to be very high.
So we don't have a search algorithm that could find that picture of it, something close to that truck?
There is not a very good defined metric of measuring similarity, perceptual similarity, good similarity in the pixel space, generally. And so.
Can you go to the next? So I'm actually interested in this question. So what are you trying to get out of this generative model in general? What's the objective?
Okay, so let me get to the model evaluation piece. Okay, so this is precisely trying to address what you're asking. Maybe just one last question, and then I
just had a question related to the previous thing. So, regarding the question of if it just memorizes, what happens if you train it on, so if the random seeds are maybe the elements are very correlated, so it's only seeing a subset of possible random seeds, and then you give it other new random seeds with different distribution?
I don't know. I think that a better way of doing things that people have done is people have looked at the conditional simulations, which is to say, condition on something, simulate me something else. Right? Things like if I condition on a sketch, can I generate a real image? Right? And if I condition on a sketch that you've never seen before, if it still generates me a realistic looking image, I might say there is something there. But let me try to address the problem of model evaluation. So let me just say that in graphical models in general, right, we have some probability distribution, we have some energy function on normalized probability, and we have this partition function. And this is an exponential sum. So things like deep belief networks, Boltzmann machines, restricted Boltzmann machines, you can't really compute the probability of X. That's a problem. This is known as a partition function. We want to estimate, we want to have some good estimate of the partition function. So in the class of restricted Boltzmann machines, you can define the energy, you can define the probability of the input, you can sum over the states of the hidden variables, can do this sum explicitly, so you have this problem, right? So this term is tractable and the partition function is intractable. So here's the question for you. Let's say I show you examples of these two models. If you haven't seen this, which model do you think is a better generative model? How many of you think A is better model than B?
With respect to which measure?
Generalization. If I just ask you, which model can generalize better? And I'm showing you these two panels.
Oh, it's a trap.
Good point. So how many of you think that this is a better model? Good. If some of you are Bayesians, you always raise hands both times. So that's right. So this, I can tell you what this generative model is. This is the generative model where I pick a training example at random and I'm displaying it to you. That's a perfectly good generative model, right? It's a useless generative model because it doesn't generalize to the unseen examples. But the examples here will look very nice, right? So when I write the paper and I show you these examples and I say, look how pretty they are, then that can be very misleading, right? because you cannot get better generative model than this one, because that's the true data, right? And if you try to, these examples of RBM samples versus mixture of Bernoullis, and if you get an estimate of the partition function, then you can show that there is a difference if you evaluate log probability, the test log probability. So in other words, if you look at test example and you say, what's the log probability of that test example, right? If the model is able to generalize quite well, it will say, yes, it has a high log probability. If it's a very bad model, it will say it's low probability. So if I give you this new example, new test example, and it tells me that this versus random image, and you say, yeah, they're both probable, then it's a very bad model, right? So let me give you an intuition of how we can do that for these kinds of models. There's a class of algorithms called importance sampling algorithms. And imagine that you have a simple, easy to sample from distribution, and you have a target distribution which is intractable. So think of a simple distribution, just like in a variational inference. Let's say these are Gaussian distributions or fully factorized distributions, something that you can compute exactly and sample from. And your target distribution is your complex distribution that you're trying to approximate. Now, under certain conditions, you can say, well, the partition function is just this exponential sum. And what you can do is you can divide and multiply by this distribution. Of course, with mild conditions, you can divide by 0. So there's certain conditions you have to satisfy. But what you can do is you can say, well, sample from this distribution. And this is just a simple importance sampling, so I can estimate the partition function. Okay? Now, it turns out that in practice, this is a really bad idea because you hit high variance. This is unlikely to work because you sample from the prior, which is, let's say, uniform, and you're trying to say how it correlates to the actual digits. Right? So typically you hit high variance. In high-dimensional spaces, the variance will be very high.
Sorry, under what conditions is that true? Sorry, could you go through?
Under these conditions?
Yeah.
It basically says the support of this distribution has to contain the support of this.
Oh, so it helps to have a fuzz. Ini is the generator.
That's right.
So have a sort of fuzzy distribution.
That's right. That's right. So typically your proposal distribution is broad. So you can even think of it as uniform distribution. And your target distribution is your complicated distribution. So you sample from your uniform distribution, you try to look at the ratio of probabilities under the target versus the uniform. Right? And that gives you the estimate of the partition function. Now, there is a class of algorithms called Annealed importance sampling, which is a beautiful algorithm developed by Radford Neal and a few other people back in the late 90s. And the idea is the following, is to say, let's consider a sequence of distributions that is bridging your initial distribution to the target distribution, right? And that sequence, for example, one way is to use geometric averages. So you take the geometric averages of your simple distribution and your target distribution. The choice, you have to specify what these sequences are, what these beta parameters are. This is the choice, has to be specified by the user. If the initial distribution is uniform, you have the geometric average looks like this. So hence the term annealing, right? Where beta here is known as the inverse temperature. And then there are different ways of, was done by Roger Gross by basically defining different annealing schedules. And the intuition is the following. If you have a uniform distribution, as you anneal, you basically anneal from uniform to your target. Right? And there are certain conditions that you have to satisfy. In other words, you should be able to draw samples from these intermediate distributions, so you have to define a Markov chain. Generally, it's very easy to define the Markov chain because you can define Markov chain in this space. You can define Markov chains and it's fairly easy to implement for a lot of models like restricted Boltzmann machines, deep belief networks. Here's what it looks like. Let's say this is your initial distribution, so it's a fully factorized distribution, which is basically counting probabilities of each pixel. Being in each particular location. So that's your initial distribution. And as you are running annealing, you sort of go through this interesting phase transition space where it kind of goes in and then digits start appearing, right? And again, what happens here is you can, after you run this procedure, you can actually estimate the partition function because it just becomes it's almost like defining a simple importance sampling defined on an extended state space. And there is a way of estimating. It typically gives fairly reliable results. Now,
sorry, what's the update rule? I'm not following this out.
I haven't shown the update rule, unfortunately. It's basically, the way to think about it is you're doing importance sampling between initial distribution and the next one. And you're doing importance sampling between the next one and the next one. So kind of like, instead of doing importance sampling between the initial and the target, you're essentially breaking the problem into pieces and estimating each piece separately. And there is a procedure for doing it correctly. So the details are not that important, but what is important is AIS provides an unbiased estimator of the partition function. So that's true. We can show it. In expectation, it gives you the right thing. But in general, we're interested in estimating the log of the partition function. Right, not the partition function itself, but the log of the partition function. And by Jensen's inequality, it turns out that if you try to estimate the log, you will most likely underestimate it. Right? This just comes down from Jensen's inequality. And by Markov inequality, it's very unlikely you will overestimate log z. Okay? So it's very unlikely you overestimate this thing. So why does it matter? Well, it matters because of the following property. It matters that if you're trying to estimate log probability on a test set, this is your log of a normalized probability minus log of the partition function. So what that means is that if you underestimate this quantity, you overestimate log probability. And that's very bad, because what does that mean? That basically means if I do a sloppy job at estimating this quantity, my model will look really good. So, if I run my code and I'm not careful about it, I'll get state-of-the-art results, basically. And that's really bad. It happened a few times when you look at these quantities, you run the algorithm, you're not really careful about how you set this up, you get really good log probabilities. And you can say, well, my model is much better than these other models. So how can we avoid this? And that's a general problem for any undirected graphical model in general. And especially if you're comparing undirected graphical models with some other models where you can compute the probabilities exactly like mixture models, that then becomes a real issue for estimating, underestimating the log partition function. And people who work with graphical models probably know that getting the upper bounds on the log of the partition function is a very hard thing to do. You can get the lower bound, but a upper bound in general for general graphical models, it's tough. So let me give you a motivating example. What are we trying to do here? Remember, in models like Boltzmann machines, restricted Boltzmann machines, you start at random, you instantiate hiddens, you go instantiate. So you're running this Markov chain, and at the infinity, you declare that this to be samples from the model. Right? In practice, what you do is you run this process for about 1,000 steps, and you say, that's it, I've converged. This is my model. Right? So when I've shown you these examples of digits, it's exactly what is happening. You're running this Markov chain for 1,000 steps, and that's your model. Right? So it's not quite the right model. It's just an approximation. So what you can do is you can say, well, forget about undirected graphical models. We're just going to unroll the whole procedure and treat this as a very deep directed graphical model where we start at random, and then we go all the way down, and what we generate is the observed data. So that's my model. My model is not an RBM model, it's this model here. And if we use an infinite number of layers, then this generative model is the same as the distribution defined by restricted Boltzmann machine. Otherwise, it's just an approximation. But generally, this is how we actually use this model in practice as a generative model. So let's look at the following procedure. So let's consider X to be the joint state of the visible and hidden variables, where V is the observed and H is unobserved. And we're going to define the following sequence of AIS distributions. So we're actually going to anneal starting from 0 all the way down to the truth, to when W is 1. Right? So I'm going to declare this to be my generative model. And this is a generative model that we call the annealing model, so it's defined this way. It's the overall stochastic process generating the data, and you're summing out all of these quantities are latent variables. So you're summing them out. So why is this interesting for us? Well, let's say we want to try to estimate probability of the test sample. Right? What we can do is we can use reverse chain as our proposal. So what does that mean? That basically means the following. It says that I have already a very good proposal for what these states should be. And because I'm sitting in a DAG model, directed model, then it turns out that when I'm estimating log probabilities, I'm actually underestimating, which is a good thing. Right? So I'm being more conservative. So now I have a forward model. And this is, you can think of it as a theoretical construct, and then the proposal starts at the data and melts the distribution, so it goes in reverse order. And now if I want to estimate the probability of the test, I can sample from the reverse. I can look at the ratio, and that's exactly what the annealing model gives me. And so if I unroll these things and use these constructs from annealed importance sampling, it turns out that I can just multiply a bunch of different things. I never need to compute any partition functions anywhere, and I can get the answer. So it's sort of, we call it the reversed annealing. So it's almost like not annealed importance sampling, but the reversed annealed importance sampling. And it turns out that we can show that this will, on average, be an underestimate rather than an overestimate. So it kind of shows the bound the other way around. Let me show you an example on MNIST. If we take an RBM model and with 500 units, and we train it on, there's one particular instance of training that as you increase the number of intermediate distributions, this is what AIS estimate gives you, right? And this is what the bound, the lower bound gives you. So there's a gap there.
Russ, most people would not know what those measures are.
Yeah, so these are the average test set log probabilities, right? So it's
And NATs, I think.
NATs, yeah. So these are based on logs. So the intuition here is the higher the number, the better the model is. Right? Think of it as almost like, in terms of coding terms, it's the compression, how much compression you can get. So if you have a really good generative model, you can compress your data much better. But what's important here is that
Why is that like compression?
Well, because like in all of generative models, if I log probability is like, it's almost like equivalent to the coding length.
Yeah.
So these numbers are basically telling you how good your coding scheme is, effectively. So this is saying that, and this is basically saying that if you do a sloppy job, if you don't use a lot of intermediate distributions, you can hit this number. You can estimate the variance as well, empirical variance, and you can say this is actually a really good model, whereas in fact it's a really bad model. So the other way to think about this is you're basically having almost like an upper and a lower bound, essentially on the estimate of log probabilities. This is still an approximation to RBMs. So this is an approximation to the undirected model, right? But at least that's the one where we can guarantee, if you're using that model in practice, you can still guarantee that that's your performance. In many cases, when we're modeling these handwritten characters, we can actually get pretty tight bounds. So in this case, we're pretty confident that both models are, the estimate of the model is, this is what it is. So it's able to generalize, and we can compare it to other models like mixture-based models or factor-based models or variational autoencoders or any other kinds of models.
What's your definition of generalization here? What's your definition of generalization?
Oh, this is generalization is really test log probabilities. So I have some test set. I compute log probability of the test example,
Yeah.
and I wanted that probability to be as high as possible.
Yeah.
Right? In general, if the model is able to generalize, it will assign higher probability to the test samples.
Yeah.
If the model just overfits on the training data, I show you a new example of like a character, it will say, well, it's almost like random, let's say, right? Then it's...
No, I'm confused. What was the previous slide? That was training, or what is it?
This one?
Oh, no, this is also test. So
No, these are all tests. It's just two different methods, right?
Yeah.
One is using annealed importance sampling, we're just estimating the partition function. The other one is using this unrolling trick and using it the other, using just unrolling it and using reverse annealing to estimate it. And that's sort of meant to highlight that it's almost like, this is what you can report in the paper and say, I'm better than all of these methods, whereas in reality, this is where you are.
Or you're somewhere in between, or that's where you are?
It's probably you're somewhere in between,
Okay.
but most likely, this is the estimate that you would report. Right? Because it's most likely you are sitting somewhere here.
Could you describe the unrolling trick one more time, quickly?
It's just basically based on reverse annealing. It's a little bit, there's a little bit of math in there, so I probably...
You start with the
you start with the data and you do reverse annealing and use it as a proposal for your generative model, which is a directed model. Right. So it's and there is a way of constructing it in such a way that the proposal distribution closely matches the true posterior. So the true posterior of your generative model. And yeah.
I'm still a little bit confused about. So you're saying that it's hard to evaluate your performance on the test set.
Right.
So that means that that's also not how you're going to use your method for real, right?
That's right. So
it's sort of proxies on top of proxies. Why don't you test sort of with a task? I mean.
So there are two ways of testing these things, right? So for example, if I go back quickly for these kinds of models, right? If I train a restricted Boltzmann machine model, one way of testing it would be to say, take features, apply to classify, and see how well it does. That's a standard way of testing these systems. Because if you're extracting some reasonable features, if it helps you in classification, you can say, I have achieved some success. But that's a very indirect way of measuring your model, right? What this procedure is trying to do, this procedure is basically saying, I have an RBM model, but there is inherently difficulty because I can't estimate partition function. It's an NP-hard problem, right? So I can use some approximations to it, like using annealed importance sampling. The issue is that if you use those approximations, then you get sort of the bound the wrong way. But if you use this approximation, right?
I'm still confused. So you're saying let's say you cannot do prediction with this model, or you cannot do compression with this model because you cannot compute
partition function. That's right.
The distribution.
That's right.
So that's not how you're going to use it anyway, because you can't.
So two things. One thing is that, yes, if you look at the original RBM model, you can compute partition function, and that's true for any undirected graphical model, right? So you cannot use these models for compression, right? But these models are still quite powerful for a lot of things. What this procedure is trying to do, this procedure is basically trying to say, can you evaluate an approximation to this model where I can guarantee you that my evaluation of the log probability and see how well this model generalizes is good, right? And I can also show you in the limit of infinite number of layers, the two models become the same. So it's a problem where a regional model, you can't use it for compression because you can't compute partition function. So you have to use some approximation. What this is saying there is another model that at the infinity will approximate the model that you're trying to train. And so maybe what you should do is, your question is, why don't you just train this model and start with this model and use that model?
I mean, for example, if you would get from your model some approximate but true compressor, right? Then you could just take the log loss of that and report that. That's something that you...
Which is generally difficult to do, right? Because for these kinds of models, again, this is basically, this is one way of let me come here. This is one way of saying, for example, if you use the original model and you try to approximate the partition function and use it as a compression, that's the original model. You get this number. This is saying that if I use an approximation to my model, I can at least guarantee that this is very conservative estimate. So one thing you can do is you can see if the two things are matching, then you have a good estimate of the partition function, which basically means that now you can more or less reliably communicate to me saying this is the performance of my model, right? So think of it as...
What confuses me is that it's the performance on a task that you actually will never do.
Not necessarily, because that's the performance of the tasks that's telling you is the model able to generalize, which is task independent. Originally you're training these models as a generative model, right? I'm generating these examples. And my task is really to try to model probability of the data, right? Try to model log probability of the data. This allows you to estimate probability, give me an estimate of the probability of the log of the data, so that I can compare it to other models. Like I can compare it to mixture models where I can compute log probability exactly, right? The difference is that these models are much more powerful than your mixture-based models or other models where you can compute the probabilities. So there's a lot of work in trying to figure out how can you train these models efficiently, because they're much more powerful than traditional mixture-based models. Right? And this is basically telling you that I can guarantee you that my test estimate of the test log probabilities are good enough so that when you compare it to someone else's log probabilities, you can say my model has better compression than somebody else's model.
So is this typical, the two curves meeting, or?
It's typical for a lot of problems, but there are some cases where the curves are not meeting. So this indicates the problem. This indicates the problem that something is wrong with your evaluation. And that can be used as a debugging, because if I write a paper and I say, look, this is what the compression rate for my model is, and it's so much better than everybody else's algorithm, then that's the problem. Most of the time we do see convergence, so it kind of gives you the sandwich, right? It's like log probability and I'm sandwiching in both ways. So most of the time we do see consistency. And when we do see consistency, then we can reliably say that our estimate is reliable.
So what I mean is, by most of the time, I mean, you take the same setting and run it 10 times.
Yes. Yes.
You will, with high probability,
That's right.
see that convergence.
That's right.
Okay.
There are sort of these error bars. There should be some error bars here. So that's exactly when you're running it multiple times. But here, for example, you do see that there is, if you use a few number of intermediate distributions, you can get very unreliable estimate. And this is the same thing for a lot of class of different models. And as I mentioned, for decoder-based models, these are decoder-based models where this conditionless deterministic neural networks, the generative model, like for example in GANs, in moment matching networks, in variational autoencoders, these kinds of models, you can use similar techniques to try to evaluate the probability of these samples, right? And again, this will tell you something about, is the model memorizing or not? Because what this is trying to do, this is trying to say, I give you a test image, and you have to tell me how good of a log probability it is. So this is something that's right now, when you look at all of these models, right now it's not clear. When I show you pictures, are they just adding a simple noise, or can they really generate new bedroom scenes? Or can they really generate new trucks or new images? And I think that procedure allows you to at least figure out what's the probability of the new image. If it's close to random, then it's a bad generative model.
No, but is it clear that somehow, if you're good in this metric, that it will look realistic? I mean, how does that fall?
So obviously, so I'm not going into too many details here, but obviously you have to induce some kind of distribution over this space. Typically, it's some kind of Gaussian noise. But in general, for some of these models, like for variational autoencoders, you are really trying to optimize log probability, right? So if you can evaluate.
I guess my question is maybe more about that perplexity measure. I mean, is it clear that if you're good in that's what you're saying, right?
Right.
That if you're good in perplexity, somehow it's good. Is that clear?
That's a good question. That's a good question. There's a lot of debate. Is that clear? Is that a good measure? Maybe not. But at least I don't know of any other good measures that would tell me, is the model overfitting or not overfitting? I don't know of any other measures where you can say, I give you a new test example. How can you tell me that the model is likely to generate this test example, or would likely to see, yes, this is probable, or this is something that's, right? It's obviously indirect ways of evaluating these models would be to take some latent space, plug into classify, and say, can I classify? But that's just one measure. What I'm interested in is to say, if I showed you this bedroom scene, sometimes I look at these images and there's like image of a horse, and it's a really good looking horse. And I say, how can they generate these images of these precise horses or precise, and what I would like to do is I would like to say, well, here's a horse, put the horse on the table. Would the model say it's probable? And if the model would say, yes, it's less probable, but it still is a probable combination compared to some random generation of pixels, then that would mean the model is able to generalize because it assigns good probability to this event.
So I guess what I'm hoping to see is, I mean, since you've run this many, many times, like models which, like that, the dog with the like multiple faces or whatever, best models, does that get low probability, or I mean?
Yeah, so it's not.
Some insight into this. Like, have you tested the perplexity?
No, we haven't tested the perplexity of these models. We are planning to. But with these techniques, what we're finding is that these generative adversarial networks, moment matching networks, variational autoencoders, it was surprising to us that we don't see that they overfit for some of the examples that we've tried.
Overfit according to perplexity.
According to the perplexity, which is already, to me, is a good sign that there is something about these models.
Oh, I agree. It's great that you can do perplexity very well. I'm just wondering about the perplexity score itself. Yeah.
Right. I mean, the scores themselves, so one of the things, about the scores themselves, the actual log probabilities probably don't matter that much, but what matters in practice is what's the gap between the training and validation. Like, if on the training I say I have, 80 knots, but on the test I say I have like 150 knots, then I can say, well, there's like complete difference between the two worlds, right? So the actual scale sometimes can be arbitrary, right, because of the noise model that you're using and so forth, but at least you can try to see, are you overfitting significantly or not, right? And that can at least help you diagnose these models. Yeah, there was a question, sorry.
Yeah, so I have a question. I mean, if you have pictures, you can use Amazon Turk to discriminate artificial ones from real ones or something.
Oh, that's going to hit 100%.
It's going to hit 100%.
Yeah, if you just carefully look at those pictures, you will see that these are not real-looking pictures. Like if you look at here, for some of these images here, you will quickly see.
But if you only show them for a short time, the trick is.
Oh, so then if you tune it, you can always have the parameter tuning, and I can give you perfect score from really bad score.
No, but I'm serious. If you would show them for a short time, then maybe you could. That would be.
Sure, but then the question is, but then again, it comes down to the point, like I've showed on this slide, right? If I have a model that just displays this to humans versus this, it's useless. If I have a model, just memorize the training data, right? What I really want to do is I really want to say, here's a test example that the model has never seen. And I want to have some measure that will convince me that the model believes that this is a realistic example. It's not the human believes what you sample, but the model believes that this is a realistic example. And yeah.
So that gets me back to, put on your Apple hat for a minute. What's from an Apple perspective, some company's perspective, what's the purpose of doing this generation in the first place? I mean, what's the ultimate goal here?
So there's actually, funny you ask it, there's a paper from Apple a month ago, which I think is probably, perhaps one way of evaluating these GANs or generative adversarial models and such is to say the following. If I can generate examples, whether they're realistic or not realistic, it's fine. If I can generate examples, new examples from a specific class, that I can then use in my model to improve my classification accuracy, then it's good. Because every time I label something, I have to pay. And if I have a model that can generate me, let's say I try to discriminate elephants from donkeys, right? If I have a good generative model, I can generate more elephants and donkeys so that my classifier improves, that is good.
Improve something else.
Improve something else, yes. So from practical standpoint, this is one good measure. It's very hard to argue against this measure.
Has it been used that way?
To some extent it has been, but it's not there yet. I don't think it's.
Is that the main application of this, or are there?
For generative models?
Yeah.
Oh, there are tons of applications for generative models. Unsupervised learning, right? So this is, I give you lots of images. You infer something about images. If I can generate images, that means that I have learned something about how the world looks around me, right? And so maybe if I have a good generative model, if I can generalize to new examples, if I show you this thing, even you don't know this is 7, your model says, yes, this is a very probable character. Then you can use it.
Good, for example, in autonomous driving or something, if it could generate something that you haven't seen yet, but you might.
Sure. I mean, a lot of work on reinforcement learning is also using generative models to generate possible futures if you're taking actions, right? So there's a lot of different applications for these kinds of models. But again, a lot of times it's very hard to evaluate them. So there is always the battle of these just are you just memorizing the training examples, or are you doing something meaningful here? So let me just quickly finish off. I have 10 minutes. Some of the open problems. Obviously, unsupervised learning, transfer learning, one-shot learning these are key problems that a lot of us are trying to solve. There is also a class of models that have to do with attention, and more recently with memory, designing external memory mechanisms, and people are trying to figure out how you can do that. Language understanding is another big area. I think that's actually one of the most interesting ones to crack this one. And there is also some work in reinforcement learning, in the space of deep reinforcement learning. It seems like we're basically taking what was done 20 years ago in RL space and reviving it right now. So let me show you some examples of unsupervised learning and natural language understanding. I have 10 minutes. There was a fair amount of work on something that's called sequence-to-sequence learning, right? So the idea here is that you have an encoder and you have a decoder, much like an autoencoder, but instead here what you're doing is you're encoding sequence and you're outputting sequence. So it's an autoencoder but based on sequences. So you can translate English to French, for example, right? And that's the representation that you're learning from the sequence. Here's one model that Jamie Kiras worked at the University of Toronto, which is to say, take a sentence and then encode the representation of the sentence. This is a recurrent network, such a way that you can generate the previous sentence as well as generate forward sentence. So you're trying to predict the next sentence and the previous sentence.
Sentence or phrase? Sentence or segment phrase?
Sentence. So this is the entire sentence. And the inductive bias in this model is to say, if I have a sentence and the surrounding pieces of sentences look the same, then the representation for the sentence should be identical for both. So if I have a sentence, I'm driving a car, or so this is like a man is driving a car, or a car is being driven by the man, then it's very likely that the next sentence in the previous sentence would be very similar for both of these representations, right? So you're basically forcing the model to say, if the surrounding sentence, the surrounding context is similar, then the representation for these sentences should be the same. So it's an extension of bag of words or word-to-vec type of systems, but based on sentences. And you can set up the whole objective is just basically the sum of the log probability of the next sentence, the previous sentence, conditioned on the representation of the encoder. And you can train this entire system. It's a just deterministic system. So we're now talking about autoencoders. You train it on 11,000 books. It's a lot of data. And surprisingly, you can get fairly good results on tasks like semantic relatedness, right? Where I give you two sentences and I ask you, do they mean the same thing or not? Right? So this is, and there's been a lot of work done in that space as well. But if we just take that particular representation without using any linguistic features or any language at all, we're just looking at the correlations in the book corpus, then we can do quite well. So here's some examples of what the model is able to do. So the ground truth is a number between 1 and 5. And the way you get the ground truth is you ask 10 people, and 10 people tell you the numbers between 1 and 5, and you average, and that's your ground truth. And the prediction is what the model is predicting. So a man is driving a car, being driven by the man. Basically, people say it's the same, and your model predicts 4.9. So a girl looking at a woman in costume, a girl in costume looks like a woman. The ground truth is 2.9, the prediction is 3.5. So you have to remember that 2.9 of 3 basically means that there is some correlation, there is some semantics between those sentences, but they're not the same. 1 would basically mean 2 random sentences. Here's an example where the model is failing, and there are a few of those. A person is performing tricks on a motorcycle. The performer is tricking a person on a motorcycle. Right? So you can see that there is a little bit of more work that needs to be done here, and the model is failing to capture that particular structure there. Again, you can use, there's a bunch of different data sets. We've looked at a lot of things, and surprisingly for us, I guess the message that I want to communicate from here is that these kinds of systems are based on a lot of linguistic knowledge. Figuring out, is the word ending on ing? What's the representation of different tokens? What's the relationship and such? These kinds of models just look at 11,000 books. It's kind of a brute force approach. And it pretty much reaches the level of performance for these hand-engineered features. Here's, I like to point out this. So one thing you can do is you can take the decoder sentence and just generate multiple sentences conditioned on the image. So the image gives some features, and so you're generating sentences biased towards the features in the image. So this was trained on 7,000 romantic novels. The decoder was trained on 7,000 romantic novels. And then you can generate, it actually generates interesting things. Like it's generating, she was in love with him for the first time in months, but so she had no intention of escaping. The sun had risen from the ocean, making her feel more alive than normal. She's beautiful, but the truth is that I don't know what to do. The sun was just starting to fade away, leaving people scattered around the Atlantic Ocean. So one interesting thing about these kinds of systems is if you look at the syntax actually looks pretty good, right? You're not making a lot of mistakes. Semantically, you're making mistakes, right? And you know, I don't know what that means. She had no intention of escaping. But it does show you that this is just a sample from the model. And obviously there is some inconsistency. The sun had risen from the ocean. The sun is just starting to fade away. So you can see that semantically we're not there yet. And that's actually quite an open problem to figure out how to generate coherent pieces of text. Even harder problem is to evaluate. Right? So that's completely an open question. How do you evaluate these models? It's absolutely not clear. Yes?
You say to use a trigram, a quadrigram, something. You have 11,000 books, right? Pull them up and match them.
Yeah, so we've tried like looking at the trigrams, right? And yes, you can generate the trigrams and it will be locally consistent, but it's far worse just visually when you look at these things. It's far worse than training the encoder-decoder.
Yeah, especially if it's different authors who have very different phrasings.
Yeah, then it's just
Trigram
basically
would be very jumbled up.
yeah. So there is at least here there is some process that generates words in sequences, and it's and there are many different alternative models for generating sentences. But in general, generating sentences, coherent sentences, is not very easy. Is not very easy problem.
Poetry would be an interesting.
Well, people using models, I think there was somebody trained these kinds of models on speeches of Trump. And it actually generates very coherent, conditionally coherent.
Sad.
But let me, let me just skip through this thing. One other thing that I want to point out is, just in the sake of time, is that there is also a lot of work right now in a language which is very exciting, is something that's called question answering or reading comprehension tasks, which goes a little bit beyond standard sort of classification of documents. So imagine that you have a document, this Germany's Prime Minister Tarsal said on Friday, and so forth, and there's a whole document, and then there is a query. US President Barack Obama will push for higher financial regulatory standards, and said on Thursday. And the question is, who said? Right? And by looking at the document, you have to answer that it's Timothy Geithner said that, right? So that requires a little bit of an effort to figure out how do you parse what the query is, what's in the document, how do you find the right pieces in the document in order to be able to answer the question. So there's a lot of work happening in that space.
So you want a bot to do the GRE test?
I think we're very far from doing GRE tests, but generally that would be the task. I think these are, these kinds of problems. I think humans hit about 95-97% accuracy if you actually solve it. Machines right now are sitting at like 60 or so. So it's there is a gap.
Actually, an interesting question is, it sounds like they have a data set with this.
Yes.
How do they produce it? Using mechanical Turk or automated?
So there are different types of data sets. Some of them were produced, some of the better ones were produced using mechanical Turk. Yeah. Because then it's the person who's sort of picking things up. So I think that this data set was a mechanical Turk. There is also another data set called Squad data set that's coming from Stanford, from Percy Liang's group, where they also constructed data sets like this using mechanical Turk. And that's actually a much, much harder task because some questions you can answer, some questions you really have to understand what's in the document to be able to answer. And so one of the approaches for doing this, you are basically encoding the documents using RNN type of models. So it's trying to encode the context. And there are sort of these mechanisms. I don't want to go over these mechanisms for too long, but there are mechanisms. In essentially, what they're trying to do is you're trying to, for every single word, like the word Obama, and the query, you're finding some kind of relationship between Obama and what the query is asking you, right? Or what Matt and the query is asking you. So it's almost an instance of something that's called attention, which basically figures out what's the correlation between the query and what you're seeing in the document. And you're trying to come up with the right representations to say this query is probably asking about this thing, and the document is talking about this thing. And there is a sort of these multi-hop architectures that read the document multiple times, refining both the query and the representation, and you get the output. Right now, most of these systems are based, again, on pattern matching, right? There is very little, to some extent, reasoning. A lot of it has to do with how well words in the query match with words in a document. And if there is a big match, that gets passed to the next level, right? So, and it gives you pretty good performance, right? You hit, this is like F1 score, you hit 70%, and just to show you the breadth of this, what was happening in the last, basically in the last 2 years, just to show you the breadth of models, what people are trying to do. And a lot of it has to do with the fact is how do you search for the right relationship between the query and tokens in the document, tokens in the query versus tokens in the document. And it's pretty exciting. I mean, you are getting 78%, sometimes you get 80%, so it's...
Human performance, you said, is 95 or something?
Yeah, human performance, humans can solve these tasks. I think maybe it's even more than that. So there's definitely some things that you can capture, but some things that require you to look at multiple places in the document in order to answer the question. It's a much harder task. Yeah, so some of these models are using some form of like memory networks, for example, and such. Yeah, so there is, but again, all of these things are just based on, so far, it's just based on pattern matching. I mean, but there are some interesting things, like for example, what's exciting about these models, and I'm almost done, is that, if I say, I put my cell phone in my pocket. I went to the Simons Institute. Question is, where is Russ's cell phone? Right. So for us, it's trivial. For these algorithms, can you learn that? Obviously, if you can handwire what that means and such, then maybe you can do it. But the question is, can you learn from the data what is happening? So these are harder things to solve. Let me just point out, let me just actually skip that. There is also, and I'm almost done, there is also this interesting class of models reinforcement learning. So for those of you, especially students, this is another area I think that's very exciting and it's picking up a lot of attention. So one of the things you can do is you can say, can you build a system that can play multiple games at the same time? I mean, so many of you probably heard about Atari games. And in general, there are these algorithms that allow you to play multiple games at the same time. So it's a single network, single model, has the same action space, and depending on what the input is, you can play multiple games. And why is this important? Well, this is important that in the sense that you can also use these kinds of models for doing transfer. So let's say if I learned, in this case, I think we've learned to play 13 games, and now we're seeing 14th game, which is the Star Gunner. And if we actually leverage some information about previous games, how actions have been performed in the previous games, then our model can, and there are a few other sort of techniques along those lines, can learn to play this new game much faster, right? As opposed to a model that's just completely ignoring all the previous games. So this model is basically learning that if there are things moving at you, shoot them, right? That's kind of what the model learns. Whereas the model that just starts, you sort of have this persistent action and you're shooting it once in a while, right? So you're still learning about the whole environment. So let me just summarize. I know I'm running out of time, but let me just point out that there's a lot of excitement in these kinds of models, both supervised and unsupervised, but I do believe that unsupervised learning is going to be the next big frontier, even though we're not there yet. It's a little bit annoying once in a while that you're doing a lot of work in unsupervised learning, and then in a supervised learning, you just collect a little bit more data and you pretty much reach the performance. Okay, let me finish here. So thank you.